Now let's see EL and OLED display. Visible light is produced when an electric current passes through a material. The terminology for this phenomena is called electroluminescence. We call EL. The return of an excited atom in organic or electron-hole pair organic material to its ground state is what produces visible light. The EL phenomena can be seen in a variety of inorganic and organic materials. The photons produced by the return of an excited material to its ground state are comparable to those produced by a laser. However, an EL device consumes far less energy and does not emit coherent light. Round discovered the EL phenomena in silicon carbide in 1907. When a current flowed through a silicon carbide plate, he saw a yellow light. Stroh discovered that zinc sulfide powder subject to an electric current emits light in 1936. However, until the transparent electrode was developed, EL could not be utilized as a light source or display. When the SnO2-based transparent electrode material was developed in 1950, EL was intensively investigated because it could be used as a planar light source. Sharp used a thin coating of zinc sulfide and mangan to build an EL device with substantially higher brightness and a longer lifetime in 1974. Many inorganic EL materials with various luminescence centers were produced after that. It was claimed in the 1990s that light may be emitted from thin films of organic materials in a manner similar to that of an EL inorganic device. Organic materials offered a variety of process advantages of inorganic phosphorus. Therefore, this report received a lot of attention. As a result, interest in inorganic EL has decreased. Instead, as a new flat panel or display, the organic EL display OLED this OLED was spotlighted. Most cell phones now have OLED screens, and the large screen OLED TVs are available. OLED is organic electroluminescence device display, or they also call this organic light emitting diode. An EL display, ELD, has at least 6 layers in its basic structure. The schematic figure of an inorganic ELD is shown in this figure. The inorganic thin film's active layer is placed between the two insulator layers. this and that. This active layer. This active layer, along with the insulated layers, are sandwiched between the electrodes to excite the luminescent centers in the active layer. So this ITO electrode and the metal electrode. So this active layer and the insulators are sandwiched between two electrodes. The transparent electrode, indium tin oxide, is placed on the top of the glass and allows light from the active layer to pass through. High electric fields accelerate the energetic electrons generated by electrodes, which excite the luminescent centers. When excited, luminous centers relax back to their ground state. Photons are released. The energy levels of the luminescent center incorporated in the active layer material determine the wavelength of the emitting light. As active layer materials, the compounds of zinc sulfide, calcium sulfide, and strontium sulfide were used. These materials' luminescent centers are zinc ion, calcium ion, and strontium ion, respectively. Tb, Ce, Eu, Sm, and Tm are some of other elements utilized as luminescent centers. Tb ion is green, Sm ion red, and Tm ion blue, Eu ion red, and cesium ion blue. Photons are emitted by these atoms respectively. The left figure below depicts the basic structure of an organic ELD. OLED's light emitting mechanism is also shown in the right figure, this figure. When an electric field is applied between the metal and the ITO electrode, so ITO electrode and metal electrode, electrons and holes from the metal and ITO electrodes are injected into the organic active layer respectively. So electrons ejected to the active layer from metal electrode and ITO electrodes, holes are injected into the active layer. Then excitons, electron and hole pair. Excitons are made up of electrons and holes. Photons are emitted when excited excitons return to their ground state. To lower the potential barrier for injected electrons, the electron transport layer is sandwiched between the organic layer and the electron injection layer. So here, electron transport layer is between active layer and electrode. The whole transport layer is sandwiched between the organic active layer and the whole injection layer for the same reason. So here is a whole transport layer is sandwiched between the ITO and the active layer. The table below summarizes the features of EL materials. Inorganic ELs have a high degree of stiffness and can operate over a wide temperature range. However, the operational voltage is excessively high. Organic ELs, on the other hand, have much lower operating voltage. The organic compounds of single molecules are altered by Joule heat. Compounds containing organic macromolecules, on the other hand, are thermally stable but have a short lifespan, but this problem is solved. The macromolecule organic air is currently used in OLED because it has several practical advantages, such as low operating voltage and a simple manufacturing process. So this column shows the organic EL, and the material type is given here, and it has strong points and strong rigidity, long lifetime, wide operating temperature, and right size screen. Weak point is high operating voltage and difficulty in obtaining a blue color, single crystal structure. This column shows the single molecule organic EL. So for green light, we have this material, blue and red, different materials. And strong point as for operating voltage is low, multiple layer and light screen and weak points is weak rigidity. And this column shows the macromolecule organic EL. So we have this kind of materials and strong points, low operating voltage, simple manufacturing process, and flexible and thin. Short lifetime problem is solved. Low efficiency of blue color. So various process can be used. Three alternative ways are employed in the ELD for full color presentation, as shown in the figure below. This figure. Making separate RGB source cells is the first way. So this way we use the red, blue or green OLED, and we can present the full colors using this separate RGB cells. NEC and Pioneer both employed this method. This method's manufacturing procedure is complicated, but the color presentation is excellent. A blue luminescent active layer and color changing materials are used in the second approach. So we use the blue OLED material, and we use color filters for other colors. TDK avoid this method. Color distortion can occur in color changing materials when using this method. A white luminescent active layer and color filters are used in the third method, this one. We use white active layer and we use color filter to present other RGB colors. This approach is now widely utilized due to its simple manufacturing procedure. Let's see the quantum dot LED. So LED, we use the color filter using quantum dots. The quantum dot is used as the emission layer in the quantum dot LED display. In all directions, the quantum dot is nanoscale. As a result, the electron is entirely trapped within the quantum dot. The energy levels of electrons in quantum dots with the size of Lx, Ly, and Lz in the x, y, and z directions are as follows. This is energy levels of electrons in the quantum dot with the dimensions, size dimensions Lx and Lx, Ly, and Lz in the x, y, z direction. And KLM represent the quantum numbers, and M star indicates the effective mass of the electrons in the material, and KLM quantum numbers. The energy levels of the electrons in the quantum dot are only affected by the size of the quantum dot as shown in the above equation. So the level is only depends on the size of the quantum dots. Okay. So that's regardless of the substance of quantum dot. As a result, the size of the quantum dot can determine the wavelength of the light it emits. The quantum dot with a diameter of 2 nanometer emits blue light. However, when quantum dot size reaches 6 nanometer, red light is released. The quantum dot is made of cadmium selenide and lead sulfide, lead selenium, and cadmium telluride compounds. Cadmium selenide is used for visible light, whereas other materials are used for near-infrared light. Several issues must be resolved in order for the quantum dot to be used commercially. To begin with, the cadmium selenide and lead sulfide quantum dots include cadmium and lead, both of which are toxic to the environment. However, because these materials are efficient at emitting light, they are commonly employed in quantum dot. For commercial applications of the quantum dot, we must develop materials that are environmentally friendly, have a high light emission efficiency, and are stable. Second, we require a technique for producing thin films with uniformly distributed quantum dots. The emission layer of the display can be made up of uniformly distributed quantum dots on a macromolecule matrix. The quantum dots in this structure should not be mixed up with one another, which requires surface modification. It takes a lot of effort to use an effective surface modification technique. Third, while efficiency has improved significantly, the quantum dot's lifetime, which is presently around 1,000 hours, is insufficient. As previously stated, commercial applications of quantum dots have a number of issues. However, we expect that those problems will be solved soon. So already solved. So we use this quantum dot as color filters in the quantum dot LED TVs, because quantum dot LED screens will take place of the OLED panel. This slide shows the operation of quantum dots on display. These figures come from Samsung display, and this figure shows quantum dot structure. It has core and the cell, and polymer coating is on on the outside particle, and 2 nanometer size, it emits blue light, and 3 nanometer is green, and 6 nanometer size emit the red color. This quantum dots can be used on the television, and QD OLED, these types of is backlight, as backlight, we can use this quantum dots, and in this quantum dot LED we use the active layer materials for emitting the photons. First, see the Q quantum dot EF LED structure, LCD structure. So basically, this display is LCD. So liquid crystal is used, and quantum dot is used for quantum dot enhancing the film, and also quantum dot color filter. So this kind of structure as LCD TV, but in this TV we use the color filter, or quantum dot as color filters. And quantum dot CF LCD structure, this is also LCD TV. So LCD liquid crystal is used, and quantum dot is used for color filter. This figure shows quantum dot OLED structure. So in this structure, we use blue OLED, and quantum dot as color filters. And this figure shows real quantum dot LED structure. So in this structure, quantum dot is used as an active layer for emitting photons. So we use the red quantum dot, green quantum dot, and blue quantum dot. That these three subpixels constitute one pixel. So that is actually a quantum dot LED. But in this structure, quantum dot is used for color filter, and OLED used light emitting layer. This slide shows the very same figures in the previous slide. Size-dependent emission wavelengths for quantum dots, and this figure shows quantum dots as color filters. So quantum dot is used for color filters in LCD TV. So liquid crystal is here, and backlight is LED backlight is used. And this figure shows the evolution of the cell phone display. First, we used monochrome LCD display, and then we use the fold shaped. It's all-in-one shape. It's a fold is folder shaped, and for display is color LCD. This is a monochrome LCD, color LCD, and now we use the smartphone display. OLED is used for smartphone display, and we can also use the flexible OLED, so you can fold the smartphone, and it's flexible OLED is used. This shows a television QLED. This QLED means the LCD TV. This is LCD TV. But here LED is used as backlight. So backlight is used LED backlight, and color filter is used quantum dot for color filters. So quantum dot EL layers, so red, green, blue EL layers should be used in actually real QLED TVs. So real QLED TVs are therefore not yet available. Real QLED TVs will soon be offered on market. Thus, this above QLED TV is an LCD TV with an LED backlight and quantum dot color filters. Currently available LED TVs are also LCD TVs with LED backlights. So LED TV is not available now. Okay, so we call LED TV, but this is not LED TV, but this LCD TV, and its backlight is LED. So we can call that kind of television as LED, but not LED. It's LCD TV. Okay, LCD. The backlight is LED. Okay. So this OLED TV, and this is display for smartphone. So it's an LCD display, and the smartphone uses OLED display. So far, we investigated various types of flat panel display, and we discussed the future display using quantum dot and LED.